Okay. So we will continue what we talked about last time. So let me just move to. So we ended to talk about like transformer. Uh, and okay, shoot, I need to find my pen. Uh, oh yeah. Oh, okay. He's here. Yeah. Sorry about that. So yes, we talk about transformer. Actually, talk about the attention models, like the paper by Banjo. So we mentioned that like if you think of the attention model, it's quite similar to the factor model like by Hinton. Oh, it's okay. Like if you don't remember that, it doesn't matter. So it's like that we have some factor models that like there's some multiple factors like you're coming in um, have some coming in signal like as a vector. And then in that factor model, like you have like a bunch of factors there. And then you're trying to match like this guy with this guy. If it's a good match, also like each of the factor have the value here like coming out. Like so I have a value and have this is a I call it query here, or maybe I do call it key here is better. Like and then you have a query here. So essentially you have the query kind of like do a dot product with the key here, and I have multiple keys here, and I will scale the output like V with the uh, inner product there. So I will just write the sum there. So Hinton has something like that like earlier, and this the attention model is essentially exactly the same thing. Um, so but I made a mistake like last time. Like actually, I made a mistake last time. For in the attention model here, we have once we have input the um, of course we are doing okay. Maybe I should go back like here. The transformer like for this transformer like original attention is all you need paper. The target problem is a translation problem. So you have like a sentence maybe in English. I don't know. I need to find something that I can translate. So again, I cannot speak Spanish. Let's say, uh, and then translate to Spanish. I say like, no, yo puedo español. Let's say. So, then for this translation here, like what you're coming in like each of word. First, we'll do a word embedding. Like as we mentioned, like we can use, for example, word to vat. Like it will become like each of this word here will become a vector of the same name. Typically, maybe 1004, 24, 1024. And for each of these vector now, we have this positional encoding. It's just adding like because I uh for the attention model is like RNN, it will attend to everywhere. For example, like if I have the attention model like get for attention layer, just a attention layer for an input here. So essentially what the attention layer does is like, okay, you think of like I have this the input, this is like the word embedding um, representation here. This is like each of the word here. And then like the output here will essentially more or less same name here. And then each part here is going to attend to each of these guy here. And also like this one also like will try to attend to everyone. And note that this operation itself does not have the time information embedded into that data here, right? Because say this guy is going to embed to just do a inner product, like do a matching with all the input here. And it will basically ignore the location of the word here. So for example, like I can have a bunch of inputs here. I can have like starting the sentence, I cannot speak Spanish, but the sentence can also be like speak Spanish, cannot I, right? It doesn't change anything in terms of this model itself. Like it doesn't really have this positional information embedded into the model itself. So therefore, we need to have this kind of like positional encoding here. Basically, just embed a code there to indicate like which one is the first word and so on. And typically, this positional code is simply like some kind of vector, like have the same name as the input here. So we simply add that there. So for example, like you have a positional, this is an example of the positional code, like for what's the size here? 512. I guess okay, the word embedding is like 512 here. So then the input here, let's say like the input size can be only have 20. So then you for the first word here, you will add this vector to the embedded uh, vector for the first word, and then this vector to the second embedded word, and then this is like the third, and so on and so forth. And this pattern, you can make it quite arbitrarily. So this is just people like made up like at the beginning. So the only thing is that like, I guess I also made a mistake like last time. I suggest I saw it, but that is actually a bit bad embedding. Uh, because you want to have the um, labeling adjacent embed the code to have to be similar, right? So to reflect that like they are similar, basically have a similar location. So um, yes, that's just some correction I for last time. So then once we have this sentence coming in after convert to a word embedding and add the positional code. Now going to the attention here. Oh yes, I mentioned like that. That's one thing I missed out last time. So now last time I simply put into the attention. The attention here will basically have three components, right? Have query, key, and values, right? So here like query, key, and value. So last time I said like I can simply put that in directly, but actually you should also like first you can say kind of more modulate your input, like the input, yeah, by some matrix here. This is simply a matrix where I do a linear multiplication with the QE key and the value, basically. So in my case here, I will start with like for the word embedding, like for basically the one getting to the intention model here, um, for the word, or basically what I want to say is like for Q, K, and V, they will be identical. They will be for each of the word there will be simply the embedded the corresponding uh, word to that the vector added the positioning code. And that will be like in as our Q, K, and V. But then they will be multiplied by a different W here. Um, and then this W here now will do a essentially maybe my QK something like that. My what I mean is that I have WQ here is my Q, WK here is my K here, and this W2W is different. Maybe I indicate with WQ here and WK here. So and also I have like this V here. You can think of it as W V here. But however, at the beginning, at least here, like we should have like Q, K, and V are identical. Yeah. So, but because this is going to be n times, right? So next time I am coming back here, like they may not be the same. Yeah. So I can have like uh different QKV coming out. Um and the multi-head embedding, like okay, this is just a single head here. For each head, I will have something like that, like as output. uh multi-head is that just like I can have like more than one of this uh component here, attention component here. So each of them we say is an attention head, and we can have multiple of this head here. So let's say if I have like two heads or three heads here, eventually we will concatenate this output together, And then like for the output here, we'll just multiply by another matrix like WCO, let's say. And then after the multiplication, the output here, we will, okay, this we will add together also this part here. You see like, this is like some kind of like a skip connection in WestNet. We have a portion of that like the VKQ here, a portion of that like will be pull out and put it back into here and add it to this component here. And after that, like I will just go for a simple feed forward layer, feed forward layer, and then just also I have a skip connection here as well. Um, and the output here, we're going back here, like again, wait a sec, yeah. So actually, if you see here, like oh yeah, I need to take it back like for what I mentioned earlier. It looks like every time I will have the same just input to the attention model here, like I have the same value here because you see like if I going back here, it's like the same thing here, like going back to here, but they will be multiplying a different WQ, WK, and WV here. So, and oh, okay, what was the remaining? Like okay, and this part like we can call it the encoder here. So this is like the encoder, and also you see there's also a normalization layer. This is like simply a layer norm here. So it's like a batch norm, but it's like normalized like layer by layer. I mean like the mean is computed. The normalization mean and variance is computed per layer instead of per batch. And so after like I go through this encoder layer or encoder transformer, so encoding transformers, then this output is plugged in here, the partial output is plugged in here. And you see like this component is essentially the same as this one here, right? So I also have, okay, maybe I use a different color and use a thinner pen is better. So this one I'm going out will have plug into the I believe it's K, or anyway, KMQ is symmetric, but I guess it's probably K M value here, like going into here. And for this part here, it's very similar to this part. We'll do a self-attention and generate a query for each of the words. So the query will come into this one here. And you see that like this one like a little bit different. This part like you see like it's almost the same as this one here, but I mentioned is like mask multi-head attention, because if you think of that like during training, of course you have the entire sentence putting into the ledger here. No yo puedo español, let's say put into the input here, but as I train like word by word, let's say I'm at puedo here. I can only see word before myself, like before this current word here, right? Because like each time like the output is supposed to output the probability of the current word here. So or I should say like for example, I'm trying to estimate this Espanol here. So I'm going to okay, I guess I Puerto is okay. Let's say I'm trying to predict Puerto here, but I don't know um uh I cannot see like I cannot see any word like after that, right? Yeah. So what I mean is I'm like at the current word here, I'm looking at is I looking at this word here. Uh but I cannot look ahead like the word like in the future. I don't know like the future is Espanol. So I cannot attend to like the word before that, like no, I'm true, something like that. So therefore, like I have this mask multi-head attention. What it is simply I will assume the inner product here with all the words like all the long causal word be after my current word like to be equal to 0. So then I will ignore uh, all the words like after that. So that will be the mask attention here. So then after the self attention, I have this query coming in here. This part is again is essentially the same as the original one, right? And then after you again like this part, I could do it n times, repeat n times, and I will just have a simply linear layer and predict the probability of the current word. So to repeat, to summarize like what we have again, like the entire thing, I should have, let's say I have this whole sentence. I just think of like doing like evaluation or like at the time we are going to use the model. We plug in the sentence here. So we have this entire sentence like we'll do a attention, a self-attention with myself, like, and then like going through this encoder board, okay, encoder side here, and it will output the query, sorry, the key and the value through here to the decoder side for each of the word. So I start with the first word here. So I should have like this. Let's see, actually. Yeah, actually, I think like the entire sentence you can put that in. So this one output like should be like have a representation of like the entire sentence as well. So for example, I have 4 words here. The output also should be 4 words here. So this one will also like plug into it, this side here. Now for this one, I will have one word at a time to kind of like output one word at a time. I can start with a symbol, let's say start. Let's say I have a start here, and then given the start here, I will do a self attention. In this case, it can only attend to itself. But anyway, like I have a start coming in, and this guy is trying to attend to each of this guy, right? And then go through the entire thing. The decoder, you have the probability of like what's the distribution of the next character here. So probably we'll have a high distribution of low, then have a no coming out here. Then now I have this part like will now get into the input again. And then this one like this, each of these will try to attend to like these 4 guys here. And then like at the output here, like we will again like output the probability, then we have a distribution for this second word here, then we'll have like most likely we have 0 here, and so on and so forth. So this is the transformer. So you have, this is the original transformer. As I mentioned, you have essentially have a encoder side here. You have an encoder and have a decoder here in the original model. And I think like they call it transformer because like you're kind of like transforming information, like the dimension of your data doesn't change. So you have like having like 4 words here. After embedding, you have like 4 vectors here, and the output also you have like 4 vectors here as well. So and that's essentially transformer. I'm like to mention a couple words like for like GPT models. Uh, GPT like is like from OpenAI. It's getting really famous. Like if you like a couple months ago, like we have this GPT-3, right? It's like super big and super expensive model. And what GPT does, like is like okay, it stands for like generative pre-training. So compare with the original like attention model here. So it it's not target to just translation. It's just trying to build a language model. So what they do is like, okay, if I have a language model, what I want is like if I input something, like for example, like what we did in the past, like in the RNN, like a couple of lectures ago. So we say like we have a language model, if you just give couple words to start with, like this is a something, then it's trying to fill up the rest of the sentence there. So in this case, we don't need this part here. We're not doing translation. We just want to have model like trying to predict the next word there. So therefore, what they did is they simply to train the decoder alone. So we have a decoder, and so essentially, uh, this is like we have the encoder erase, and we have like this part like for this uh, key and value. We'll just like also have this part like connect to this here, right? So then this is essentially GPT model. Um, but of course, you just train a very big model there, and and you can use um you can uh you can use that like in many applications, as you can see, like even though it's just a generative model, uh these are some examples that you can use the generative model like to say do just classification, like this is a sentiment classification. So let's say you have like pre-trained a model now. So what it does is like, okay, I will give you um some input task here. After training that, like I'm going to do a prediction, and then like after wait a sec, test prediction task classification. Oh, okay. Yeah, this is just showing that I multi-head, right? So I can, okay, for training, of course, I can just train it to for test prediction, right? I will just do a test prediction. But like all these machine learning models, in neural network models, I can just say ignore the last layer. I can take the second last layer as features. Now, after I take that, like I have this transformer, like if you see here, right? I used to have like this linear layer and softmax, but I can just take this, or like even the earlier one, maybe okay, or like I just replace this layer for this for different applications, right? So for example, I can pre-train another linear layer here to do classification, like for example, sentiment classification. Now I have a sentence coming in. Instead of like getting using the original linear layer, I'll train this linear layer to just classify the sentiment of the sentence. So whether it's like positive, negative, or anything. So or I can do entailment, like in the sense I can have like two sentences like kind of separated by a delimiter. And basically, I have the first part is a premise, the second part is a hypothesis. So if the second part is a consequence of the first part, then we'll say we'll just output kind of like classify one, otherwise we'll classify it into zero. So then again, I will just train this linear layer to do this entailment. So and we can do similarity kind of to find the similarity of two sentences. So I can like this one. We have almost like a Siamese lateral here. So actually, it's a Siamese lateral because I have the same transformer here, right? But I put in two different inputs here. One is I have like two tasks here. I want to see if they are similar to one another. I will put in one like just in order in the original order, and then the second one I will just flip the order. And then afterward, I guess I train the linear classifier to determine whether they are similar or not. So this will have a lot of application, like for example, in managing like online forum, people are very creative to ask different questions, or like I should say, ask the same questions in different ways. So this will be like very useful, like to identify like if the same question have been asked before. And we can also like do this kind of multiple choice, like Q&A, like we can have like, let's say, put in the the context here. It can be include like both the maybe just the question here, like we can ask a question, or like and try to see like what's try to predict the answer here. Most likely, like the context should include like the information uh, that is needed to answer the question, and then like we have the corresponding answers here. Then just similar to the earlier case, like we can just train um, this linear layer to uh, find out like which one is the correct answer. So for example, like this one is like, uh, wait a sec. Uh, yeah, this looks like they have a different linear. I think like, yeah, this one I'm not sure. Yeah, to me it seems like I can share the linear layer here, but it just uh, shown as like they have like different linear layers. Yeah, that I'm not 100% sure about that. So if they have like different linear lasers, it seems like you, uh, yeah, it's okay anyway. Right? So okay, that's for GPT, and like you can use some GPT for some applications for GPT here. And there's another like very famous model like using transformer known as BERT, and it's like a bidirectional model. So for GPT, like because like you are training a predictive model, right? So therefore like it cannot be bidirectional. What you're training is like just predict the next character, right? So what they did like for the BERT model is like, okay, like I just want to have a language model, right? Why I really need to constrain myself to be a predictive model, like always like predict the next character. Maybe I try to just generate a model like just to fill in the blank. So this is exactly what they did. So what they did is like they create some tasks here. This is some p-test task to train this model that they will just input some sentences here, and more precisely, like, oh, where's that? Yeah, he will put in the two sentences here. Uh, so we have the start character, like, okay, or start symbol to indicate this is the beginning of the first sentence. And then we will put a separator to separate two sentences here. And in the sentences, they will also like mask out some of these character, some of these words here. And the model is supposed to predict the word here, so from the sentences here. And also like besides this task of predicting this missing word here, they also like have this subtask here, uh, sub p-test task here, like trying to do the entailment, to solve the entailment problem. So we want to see whether like the second sentence is actually really kind of like a logical consequence of the first sentence. So, and of course, like for this kind of stuff, you, apparently you can do like self-supervised learning in the sense like you don't need to do any labeling, right? So we just pull out sentences from Wikipedia and then randomly mask out some of the words there, and will be my training data. And if you pull out two consecutive sentences, then we expect that like for the next sentence prediction, it will be true, right? So, and if we pull out like one sentence, say from one paragraph, another sentence from another paragraph, so we'll expect that the outcome like for next sentence prediction should be false. So all this we can generate, or in the sense like log next. So we can automatically generate labels for training. So then like after this uh, training for the BERT model. So okay, maybe I forget one thing. So because we are doing the um uh not doing the predictive model here, right? So instead, like when we are doing BERT, so we will simply use the encoder part now. So we can ignore the decoder part, but we just have use the encoder part, and maybe to train the model basically, right? So and the encoder once you get the uh output. Oh, wait a sec. Let me. That's one thing I forget. So, for the for the p-test task here, Of course, I can put the BERT model like with a okay, but it's not something major. Like you can double check that in the original BERT paper. So what I'm thinking like okay for this one, okay, I'm guessing like most likely is that like for the BERT model, so I should have just use this encoder. Right? Afterward, I still go for a linear layer, and the linear layer will try to answer the two questions there. Like basically uh, yeah, I think I definitely need a linear layer, of course, because I'm going to predict the missing words, right? So the missing words here will have a uh okay, will be like include all the words in the dictionary, right? So here like I need to predict the missing words here. So I I can have like multiple branch here basically, right? So for example, like okay, I have my naive imagination may not be the correct one that people did, but I guess that's fine. So um I may have like as you can see in the p-test task like for the BERT model there, we're trying to do two things, right? One thing is trying to fill in the missing word there. The another thing is trying to predict whether one sentence is the entailment of the other sentence. So I can basically put three branch out, right? And basically, like for this one, these two linear layer here is going to predict the words. So I will have like the length of this linear layer, the output of this linear output dimension of the linear layer should be the total dictionary size, and then I can get the distribution of that, right? So this will be like, for example, like predict a word, like for example, like this one is likely to be milk, like there somewhere. So and then like this will predict like the missing words, two missing words here. Um, and also like I can have another output like, to do the entailment here, maybe another linear layer or like yeah, we can do another linear layer basically. So anyway, but after training that, like this is like the training the p-test task, right? After training that, like we can remove these linear layers. We don't need the linear layers anymore, but we just take the encoder out. The encoder, this transformer part, like as I mentioned earlier, the input dimension and the output dimension will be the same, right? So then I will have like an illustration like this here. So I have the BERT model after the training. So I will have something like this. Like if I have some work coming in here, this is after embedding, like put into the BERT model. I have the output dimension is the same size here. Uh, then we can do some fine tuning on this BERT model here in the parameter of this model here. And we can do like several different applications using the BERT model after fine tuning. So let's say I can do just was uh, so we can do okay. Let's see. So we can do like at least some classification tasks here. So what it is like for these both cases, I will okay. I see like what's these two difference here. So okay, I can do like for example like this can be like some sentiment classification like we mentioned earlier. So we have one sentence coming in. We'll just take the first one, first output like as the class labels, like whether it's positive or negative. Then we can like fine tune the model such that like this will give out the sentiment of the sentence. Or like we can do a, for example, like again entailment uh, this kind of problem. Let's see like if like the second sentence is a logical consequence of the first one. So again, like, after we have the BERT model, we can fine tune the parameters inside just to have the first label here to say the first output coefficient to say whether it's a first sentence is related to second sentence or not. Um, we can also like do something like more non-trivial like application. For example, I can do a Q&A task here. Uh, for example, for this squad data set, it will include like um, a question here, and then a paragraph here as the input. And typically, like this answer of this question should be included into the paragraph. So what we can train here would be we will train a delimiter somewhere. I'm just saying that, okay, after I have an input here, I will have, um, I will train the output here that such that like uh, one of these will be output like as a start symbol, and one of these is like as a and and symbol here, and then like then we can identify like where we should start and where we should end. Um, or we can also like do tagging. This will be like name entity identification, like that's basically given a sentence you want to know like what's the um, what's the category of the each of the word. For example, like whether um, it's a name or it's a place or it's an action or something like that. So and for that one, it's very similar to semantic segmentation in basically image application and computer vision applications. So that's good. And one remark here is we mentioned positional encoding like in the transformer model. So and we can also have like this is a positional embedding earlier. We can have like extra embedding is like uh, for example like for the segmentation embedding here, segment embedding is like to indicate that like this is the first sentence, like this is the second sentence. Um, yes, okay. There's some other models. It's kind of dated. I found a blog post from Wikipedia. This doesn't include, like, for example, like GPT and so on. But in remark is like all these are really, really expensive. I remember, for example, XLNet, it's like it costs a house and to train basically. And for GPT-3, of course, it costs millions even. So but the nice thing is that once you have the train model, you if you just need to fine tune it, or even you don't need to fine tune it, but you just use it as a um, kind of like directly, like you can still able to solve, at least give you some very rough solution to handle some NLP problem. For example, like uh, there's some interesting application is like if you give some input, like for GPT-3 model, you can input say um, an example sentence, like a translation example sentence, like for example, first put the English sentence, then puts in the corresponding Spanish sentence, and then put in another English sentence again. So the model, okay, it may or may not will give you the translation of this sentence, like the second sentence sometimes. Or like if it does not, then you can also refine it somehow. So okay, anyway, like this is a for transformer and attention models. So I guess like the next thing I like to talk about is I need to find my mouse. Oh, okay, I see it. So I like to spend some time to talk about capsule. What is a capsule networks? So I guess it's a nice follow up with like attention models. Because I think it's very similar capsule networks. At least idea wise, a high level idea wise, there's many things similar. So what capsule network does, or like you think of like what uh, neural networks in general, like if you just think of like a classic CNN or just a plain vanilla like neural network is missing is that like you can think of the neural networks is really composed of neurons, right? So each of them is just a neuron, and you have a nuance, like you have inputs coming in, and then you have output coming out. This is just a weighted sum followed by like a activation function, right? And oops, yeah, and and because this is a for the single new one here, each of the inputs is scalar. The output is also scalar as well, right? So this is just a scalar inputs coming in, scalar input going out. And if you think of like the information represented by the output of this new one here, it's pretty limited because it's just a scalar unit, right? Just a scalar value. So the idea of capsule is that like maybe we can like group some of these related neurons together as a unit, and now the output of this capsule now will be like a vector, right? So because it's a vector, then it will have like a richer representation. It can represent something like uh, in the more high level. Um, for example, I may have a capsule that like correspond to a mouth, and I have a capsule correspond to a nose. And so, but of course, this is kind of similar. You can think of like in CNN, you can also think of like a unit like in CNN there, like is kind of like have multiple idea if that new one. But be careful, there's a caveat here. In CNN, of course, the output of a particular new one, if you trace it back to an original image, that that new one or like that those pixels that would be like related to this new one will be more than one, right? That would be like an entire patch is going to be. Remember, like we're trying to visualize CNN. If we say like this new one, or so it's a particular new ones here, like what um what portion of what region of the image actually will activate this new one. We say that like okay, if we go back, we try to visualize that maybe like there's a there's a phase here. This phase will kind of activate this new one, right? But the thing is like even though the phase is likely, okay, this is not a phase, this phase is likely to activate this new one here, but the representation of this new one, the output of this new one is just a scale value, right? It has very limited like capability in representing like the information here. It's just we just know that okay, this kind of things will activate this new one, but apparently like the information of this thing here is not embedded into here. I have this one is like totally high dimensional objects. This one is just a scalar value, right? There's no way this is embedded into here. So therefore, like the idea of capsule is like fixing this issue here. So if I have this capsule here, it's really I have a vector representation of this output, and this have can essentially have captured like the entire information of this phase potentially, right? So then I can have like for example this phase capsule, not just like a phase will activate this capsule, but I can have the output of this phase capsule actually encapsulate the information of the entire phase even. And also like I can have like here I have the mouth capsule, nose capsule, and so on and so forth. Now another thing about the vector representation is that like once I have the vector representation here, I can do something that's not possible in the original feed-forward neural networks. Because if you think of the original feed-forward neural network, it's always just moving forward, right? So it just always what should I say? Uh, okay, let's see if I can find a nice example later. Uh, okay, okay, maybe just for fun, like maybe I will ask a participation question, like Well, it should be like everyone, but uh, anyone see this picture before? Like not seeing this picture before, maybe I should ask. And anyone never see this picture before? Like anyone's kind of like, I just want to see if you guys are still around or like. Oh, actually, I have someone is no. I didn't expect. Yeah, okay, I don't expect that. Like, so, oh, okay, this is a really famous picture. I guess um, probably, I don't know. I saw that like probably elementary school or something like that. I don't know. I don't exactly know the name of this picture. So, but it's a famous illusion. If you never see that before, what do you see basically? I guess like you can either see it as a girl or you can see it as a it's a girl, like you see the ear here, right? It's turning the face and looking at that way. Or you may see a kind of an old lady, like have a nose here, and then there's a eyelid here, and then her eyes here, her eye here, and then her mouth here, and so forth. So what I'm saying is like, depending what you see. So you see the old girl okay, when you see the old lady here, then you would think this is the mouth, right? So in the sense that when you see the old lady, actually, you are also like what I want to say is like, if you're doing feed forward neural network, you essentially your feed forward neural networks will just determine, okay, this is something like that. This is the mouth, right? And this is the mouth, and then I based on this is the mouth, then I look at the entire one. I decide that she is a old lady. But on the other hand, like if you take this as a when you observe that this is actually is a young woman here, young girl here, then you won't see this as a mouth, right? Maybe you look at this picture again. So what I mean is like at the time when you're seeing that this is like whether it's a young lady or like young girl or like an old woman, then you change your perception of like what you're seeing here. You consider this is like either an eye or like a ear. But for feed forward neural network, apparently there's no mechanism for you to adjust what you already decided what it is. For example, if you have like a layer of like CNN, like one layer at a time, you once you do the observation or do the prediction here, this is the ear, then this is the ear, right? But it's not like if you go all the way based on the other information, maybe you go all the way and decide that this is actually an old lady, then you should back propagate somehow and now determine that okay, this is actually a year instead of an eye, something like that. Know that like okay, during training you have this back propagation, but during evaluation there's no back propagation here, right? So after training, as you can see, like the neural network model or the classical CNN model does not emulate what people have for the human vision system. So is that reasonable? So therefore, like this is another thing that is kind of trying to be addressed by capsule networks. It's that like we should have something they call it kind of a dynamic routing of information. You can think of like classic feed-forward neural networks. The routing is static, right? Because once you're training the model, the weight is fixed, right? The weight is all fixed. So you will always say, if I have the weight like this, I have like, this is my mouth score or whatever as a vector. I'll just simply multiply by this W and continue to feed forward, right? And this W is not going to change regardless like what kind of input you're putting into the as the image, as the input image. But on the other hand, like now for the capsule network, because you have the capsule is actually a vector representation for the output. So what we can do is we have the output of each of the capsule here. We can kind of like try to use based on the vector, we can try to match whether this in the next layer capsule, whether it match well with the earlier layer capsule. So if it matches well, then we will assign a higher weight. So we can think of this, it will be higher weight. Then we can allow more information to pass from this mouth to this face here. So if it doesn't match, like for example, if this eye here doesn't match with this guy here, then I will allow only less weight here. So therefore, like this will be like a have kind of like some kind of like dynamic routing. And you can also see that this is similar to attention because attention is doing something similar, right? For attention model, we also like have two sides of the attention layer. We see like whether this match well with this one. If it matches well, then we will have like this factor, like if you remember. So we have V, essentially V, K and Q. If it matches well, then it weight this one with this VI, right? Something like. So if this KI match well with my Q here, so then this weight will be larger, right? So then actually it's a very similar flavor here. The main difference here, if you think of the attention is applying in the same layer here. You can think of like, for example, if you have two sentences here, like in an attention model for NLP, like I have one sentence here, I have the same sentence here, like doing self attention, like a capsule process, something like that. Then I have each of these words I'm trying to attend to same thing here, right? So you see, like this in terms of semantic level, like the two sides on the attention layers, like input and output sides are actually at the same semantic level. But on the other hand, like for the capsule lateral, one side is more like high level um, than the other side. So typically the next layer will be higher level. So and how we're going to attend like from lower level to high level, what typically it does is like if we have a model here, if we have a representation here already, so we again I do something very simple. We can multiply by matrix, right? Transform this to this high level here, and then so what's going on is here, like we can think of they have capsule output, like for each of these capsule here, maybe I have this x1, x2, x3, x4, x5 here. Now I'm going to translate to the higher layer here. First, I multiply to some W here for each of these, some P-training W. Note that this W is like different from the weights that we have earlier because uh, this W is like for the translation, but the actual weights you see will for the dynamic routing will depends on like the matching, right? So I have, let's say this is W1 here. I have X1 W1, and for this second one I have W2 X2 and so on. Now for this capsule here, I will have an initial estimation of the uh, capsule output for this guy as I just weight the sum of them, right? Or initially it would be just simply Wi, Xi, right? Sum of them. This is my initial estimate. Maybe I call it Y zero here, right? Now with this one here, now what we can do is we can do the dynamic routing now. We have this representation for this guy. Now we can go back and redo this again. Now we have X1 and I again multiply by Wi here, multiply by W1 here. And but now I'm trying to see whether this match well with this guy, right? And if it matches well, then I will have a higher rate basically. So, but it won't. It's not exactly the same as the attention here, attention there. For attention, we'll be simply doing an inner product and then multiply by this WIXI, right? So here it did a little bit more sophisticated, like for the original capsule level paper, as you will see later on. So, but this is the main idea basically. So, you can see that like this will be an iterative process, right? So after I update the weight here, so update the weight here, so I will have a new estimate of y here. I will have like, let's say y1 here, right? Now I can do y1 and again, like trying to match with like all of this x again. So then I will have another scaling, another uh, dynamic route for each of the capsules here. And then I will have another update y2 and so on. So we will iterate several times. And then you eventually we have the final y there. So you can see that like quite differently from attention lateral also like this, the routing itself is actually iterative. Or even though there's some non-intuitive routing approaches, but at least for the original two um, capsule paper by Hinton are both uh, basically at interactive routing, iterative routing. So this is just repeat what I said, like the routing rate is not fixed, right? So it's like not like classic CNN is fixed, right? So this therefore is like kind of data-driven routing. So it's like kind of similar to the attention network also. And it's going to do this routing by agreement. So we want to like have like the later capsule, sometimes we'll call it the parent capsule, kind of match well with the earlier capsule. If it matches well, then we will say this agreement, so therefore more information will be passed from this child capsule to this parent capsule. Um, and this illustrates the idea again. Like this is like I kind of like borrow slides from a very well presented video like online. I forgot about who now, but if you Google like capsule lectures online, most likely this will be the first video coming out. He gave a very nice illustration here. For example, I have a boat here, so just have like two simple components like to draw this boat here, and then like I have a rectangle, I have this triangle to correspond to the sail, um, and then basically the capsule, you can see like I have this spool arrow correspond to this triangle here, and then the black back arrow correspond to the rectangle here. And so because the capsule, because the capsule, as I mentioned, is a high dimensional uh, object here, right? So it's not just a scalar, or it can be a vector. So therefore, it can represent not just the intensity, whether there's a cell here or that, whether there's a rectangle here or that there's a triangle here, but it can also store the orientation information. So for example, like for this input image here, if I go through the capsule layer, the first capsule layer, trying to classify like this triangle and rectangle. So in a very ideal case, as you can see here, you find that there's a rectangle here, right? So therefore like a high kind of activation, like for this like back arrow here. But also you find the orientation of that rectangle is okay. The rectangle is like oriented this way. And similarly, there's also a triangle like in the same location here, or like in around the location up above it, and it has an orientation like this one here, right? And now you can see like if I change the orientation, supposedly my the representation of the capsule should capture that as well. Therefore, like Hinton called this like equivariance. He claimed that like the original uh, CNN is only invariance because the original CNN is doing like polling in the laterals, right? So for pooling, it basically it will just erase, I should say not erase, but remove the remove the orientation information, or yeah, this may be a boss joke to say that. Uh, but yeah, but what I mean is like, yeah, I guess it's like, it's kind of fair to say that because uh, if I have some object here, let's say if I have object here, if I do I do pooling now. Uh, what pooling does is like it will downsample somehow the image, right? So therefore, like maybe in the earlier layer, I know there's an object here, but after pooling, like I'm not sure that object is actually here is here anymore, right? Because like what pooling does is I may have like okay pooling over like all new ones like earlier like in this region, and I just get the maximum, right? So the orientation or like the position information will be gone, right? It just know that okay, I have the maximum value later on. I know that the maximum value among all these um, will be some value here, but the positioning or the location information will be discarded. So, but in terms of capsule, like if we don't do pooling, uh, so ideally, theoretically, we don't have uh, the position information and also the orientation information discarded. So therefore, ideally, we should have something like this. So the capsule not only have identify whether the object existing, but also like can capture the orientation information as well. So and oops. Uh, this slide is actually quite useless. I guess I just mentioned that there's a squash function. So to ensure robustness or like the stability of the model, usually like we apply some kind of squash function just to um, make sure that the output layer of the capsule, output of the capsule uh, to be like between 0 and 1. We have like magnitude between 0 and 1. So, but we don't want to just normalize that because the the magnitude itself have contains some information. It's still like if the magnitude is big, it just say that it's more likely. That's more likely. There's an excitation there. Um, so, but we don't want the value to be shoot to the moon also. Um, so this I mentioned like earlier that the the key idea of a capsule lattice is like for every capsule, like in one layer, it's trying to predict like every capsule in the next layer. So I have a face capsule here earlier, if you remember, like I have a mouth capsule, an eye capsule, and so on, right? I have a face, like this like trying to predict whether it's a face. But I have this maybe a human face. Maybe I also have a cat face here, right? And I try to like this also will vote to this cat face capsule, like from each of this child capsule as well, to determine like which one is more likely to have a good match with this cat face here. So if we go back to this simple example here, let's say we have this originally the earlier layer, we have like the rectangle capsule and the this triangle capsule. And then in the next layer, I may have a boat here, but also I may have like a house here, right? So we're trying to see like whether this actually is a house or a boat here. So then we're trying to match this rectangle and triangle capsule with each of this boat and house. So now I have this rectangle capsule is will predict that the orientation of this boat with this way, right? Because this rectangle this way, the boat will be this way, right? And similarly, it will predict the house orientation will be like this way. Um, and then like for this one, oh, and also by the way, this is the W I mentioned earlier, right? So for the U capsule, this earlier capsule, like UI, uh, like it will be like the child capsule, like for example, the rectangle capsule multiplied by W. I have this WIJ here, just indicate that like this is from let's say from a rectangle capsule, a rectangle with the index I here, let's say, uh, and then like it kind of trying to predict to the house capsule, like the J is like with an index house here, right? Then I will have a prediction for like UJI, let's say, and I eventually sum all this prediction together. So, but we'll see that later on. So now, um, I just mentioned that like we trying to predict whether it's a house or a boat like based on the rectangle capsule, right? Now we look at this triangle capsule now. For the triangle capsule, for the boat here, we will kind of estimate in the same orientation, right? But we're trying to estimate like a house here. You see like for the rectangle to be this direction, the house must be upside down, right? So now what we see is that like for these two guys, we have a strong agreement, right? So therefore, like the the um the um the routing weight there will be reinforced, right? For the rectangle and the triangle capsule, like route to here will be reinforced. But on the other hand, this one does not have a good uh, the house does not have strong agreement. So therefore, like eventually the routing weight from the rectangle like to the house here will be diminished. So therefore, like eventually we will decide that this is actually a boat instead of a house. And okay, I can skip this K-mean. I don't think like you need this to explain this. So here's a more precisely what's going on, like with all the detail of the first um, Hinton's capsule paper. So this is like the child capsule, the earlier layer capsule, and this trying to predict the later layer capsule. You can think of this of the child capsule, like for example, this is a triangle and rectangle. This has a one is a have a boat, and this one has a house here, something like. Um, and so to start with, like this child capsule is trying to vote for like each of the parent capsules, right? So as I mentioned, like, you're trying to multiply for this W matrix here. It's just like a post-transformation matrix you can think of. Like it should be pre-trained somehow, like during training. So after I have multiplied by this W, I have this estimate of this first capsule, like based on the first child capsule. Uh, and originally, the weight here, okay, basically I have this UIs here, and basically I have this estimate of this V, as you can see, it will be like for the parent capsule, it will be a weighted sum of all this U here, right? It will be weighted sum of U1I here, weighted by the CI1 here will be the routing weight from capsule, for example, CI1 will be okay, or C21 will be the routing weight from capsule 2 here, child capsule 2 here to parent capsule 1 here. So initially we will have all these uh, weights here will be the same. CWI will be CI1 will be the same because it's like basically trying to estimate whether they matches or not, right? So with no information, we will first assume that they are to be the same. But then like you see, after I estimate this, I have this V here. Now I can see whether this V match well with each of these U here, right? So then I will just take V and U, basically V and U here. They have like V and U do an inner product here, and I will add with like this Bij here. So this Bij at the beginning will be just zero, but each time I will just kind of like accumulate it with this inner product of Vj and Uji. Basically, how matches is Vj with Uji here. And then once we update this Bji here, we can do a soft max uh, of B to obtain C here now, right? So for example, like if you see here, I once we updated um, Bij here, so out of like this several branch here, now this two looks more similar, like this two child looks more similar to this guy here than this one. Then therefore this two will have like a higher weight, right? So we'll have like more information to flow from here and here than from here to V1 here. So similarly for this guy here, maybe I have like now this one is stronger than the two here, so I will have more U's. I mean, in the sense C1, 2 will be bigger basically. So this will be like this process will be repeat like many times. Then that will be the uh, yeah, basically the evaluation like for the capsule laterals. So this revisiting the toy example here, um, I guess I probably can skip it. Let's see. Yeah, I guess I can skip this. It's essentially repeating what I said. So by the way, doing training, you can see like if we look at the loss here, if I have multiple classes, um, I should have V essentially you know that like for the first Hinton capsule paper, they have the V, the output of the capsule essentially like the magnitude itself represent the activation, represent how excited is the capsule or how yeah how relevant is the capsule. So so therefore like if I use that like for classification, let's say if I have K classes, I probably have like K capsules at the end, right? And then I if I is classified as a dog here, then the dog capsule like should be most excited, like should have like the highest value compared to the rest, highest magnitude I should say, because all these capsules is a factor. So during training, uh, you can see also like okay, and also know that like for capsule like I mentioned that like we have a squash function like after um, updating the capsule. Right? The squash function will kind of compress your capsule output like to zero to have magnitude from 0 to 1. So if you have multi-class here doing for doing training, so we have a loss here like kind of a some you can see like this is a nice trick probably to maybe usable like for other problem as well. So what it did is if you look at the translation, like these things I was saying here, it's basically trying to make sure that like if I, for example, like if the ground truth is indeed a dog, I want to make sure that the dog capsule will have the magnitude at least point 0.9, and I will have the rest of the capsule to have like no more than 0.1 here. And you see how they did that is I basically have the this is the this is basically 0.9 here, right? This is 0.9. So I will have like 0.9 minus the ground truth capsule here. So if like this one is larger than 0.9, then this one will have give you a loss 0, right? Otherwise, I will have a non-finite loss here. So similarly, this guy here, I will have like VK for the rest of the classes here, not the ground truth class, minus like here, like this is 0.1 here, like n minus is 0.1 here. So if this one is like bigger than 0.1, then this will have some loss, right? This will contribute some loss. Otherwise, there will be low loss here. So that's like how they conjure a multi-class margin loss here. And of course, you can also trade off this lambda here, but in the paper, it's just use lambda is equal to 0.5. And for the net loss here, like besides that, you have this margin loss like that we just mentioned. We can also introduce a reconstruction loss. It's like after you create a capsule representation like at the very end here, right? So this is a capsule here. You can just take back the capsule. For example, you classify to dog, right? So then you take this one and try to reconstruct back the original, say. So if you and then compare or this reconstruction with the original, so and see if this is like close to one another. So then during training, we're trying to minimize this net loss. So will be the margin loss multiplied by added with like this alpha times the reconstruction loss, and this alpha like in the paper is just this pretty small value 0.005, 0.0005. I guess that's already time. So I guess I'll continue to talk about capsule laterals next time. Um, Maybe with more detail. Like with this one, I'm also like hinting say second capsule lateral paper. So yeah, I will see you guys next week then. And if you guys don't have any questions, then I will just stop the uh, stop the uh, video now. Stop the connection now. And by the way, make sure like okay, it's okay. I guess I will talk about that later. So yeah. So okay, I'll see you guys next week then. Yeah.